we are going to write down the structure of the set of discontinuities of a function f from R to R. So before that, let me just introduce terminology which is useful. Definition: a set capital F subset of R is said to be a F sigma set if it is a countable union of closed sets. Recall that a intersection of closed sets is always closed and a finite union of closed sets is closed. So a countable union of closed sets need not be closed. I have given an example before. So a countable union of a closed set is what is known as an F sigma set. A countable intersection of open sets is called a G delta set. Okay, the terminology is a bit weird. I think it comes from the notations used in German. I'm not 100% sure, but this is just something that has to be learnt. We have to live with such terminology. Okay, so I can state the theorem. Let f from R to R be a function, then the set of discontinuities of f is a F sigma set. So you cannot have arbitrary sets as the set of discontinuity. The set of discontinuity has the precise structure as the countable union of closed sets. Well, the proof is rather simple. Well, D, the set of discontinuities, is just union of dks, where if you recall, dk is the set of points x and R such that oscillation of x of the function f is at least 1 by k. Okay. Now each dk is actually closed. Well, why is that the case? Well, if xn converges to x, and xn are in dk, then if you look at diameter of f of x minus delta x plus delta, if you look at this diameter, this also has to be greater than or equal to 1 by k. Why is that? Because some xn is an element of x minus delta, x plus delta, this open interval. Some xn is a member. Then if you were to choose diameter of xn minus, let's say, delta 1, not diameter of xn minus delta 1, diameter of f of x n minus delta 1 comma xn plus delta 1, such that this closed interval xn minus delta 1 comma xn plus delta 1 is fully contained in x minus delta x plus delta. If you choose it like that, then this diameter will also have to be less than 1 by k. If this diameter was less than 1 by k, then this diameter will also have to be less than 1 by k, simply because this is a subset of this set, right? So this shows that x must also be in dk. The oscillation at the point x cannot be less than 1 by k. If it were, then for points this xn, which is very, very close to x, will also have oscillation less than 1 by k, which is simply not allowed. Okay, so this shows, and in fact that's done. I don't even have to write anymore. So each dk is closed. Each dk is closed, and we are done. And we are done. That was a rather easy proof. All we had to observe was that these oscillations behave nicely with respect to taking limits. Okay, we get a nice corollary of this. Nice corollary. The set of discontinuities, of a function f from real numbers to real numbers cannot be the irrationals. You cannot have the set of discontinuities to be exactly the irrationals. Well, proof. If irrationals were an F sigma set, then R is a countable union of closed sets. Why is it a countable union of closed sets? Well, Q is a countable union of singleton sets which are closed. Q is countable. So irrational numbers are also going to be a countable union of closed sets because it's an F sigma. We are assuming that it's an F sigma set. That's the definition of an F sigma set. But each of these sets is nowhere dense. Well, that's obvious because irrationals don't contain any interval. If you write irrationals as a union of closed sets, none of those closed sets can contain an interval. Obviously, singleton sets do not contain any interval. Therefore, these are all nowhere dense sets. This contradicts Bayer category theorem. This contradicts the Bayer category theorem. Okay. So, we have now shown that the set of singularities, the set of discontinuities of a continuous functions cannot be arbitrary. For instance, you cannot have the set of irrationals as the set of discontinuities. This is a course on real analysis, and you have just watched the module on the structure of discontinuities.